Hey guys, what's up? So in this video, we are going to talk about existence of a representative consumer. So throughout one's economics education, they will often see the following problems defined in this way, which is maximizing some utility function subject to a budget constraint. It's natural to go and ask, is this a valid way to go and think about welfare and demand? In this video, we're going to go and talk about this type of thinking. So before we go and answer those questions, we have to have some definitions. So our first definition is that a positive representative consumer exists if there is a rational preference relation on our commodity space, which is defined by a real number line in L dimensions, such that the aggregate demand function, x as a function of P and M, is exactly the Walrasian demand function generated by this preference relation. Practically speaking, this means that the demands we observe in the whole economy could be generated by some fictitious individual. Okay, the next definition that we're going to have is that of a social welfare function. A social welfare function is a function which goes and maps real numbers in I dimensions to a single dimensional real number space that assigns a utility, a value, to each possible vector. So you have a vector of utilities in Ri for I consumers in the economy, and it goes and it spits out one value. What we end up going and having for a social welfare function is that it takes in all these utilities from all of our individuals and it spits out a number, right? Which goes and makes an overall assessment on the welfare. Now, given our definition of our social welfare function, we're going to say our planner solves the following distributional problem, right? Which is just, it's the same problem that we have here, which is maximizing this social welfare function, but this time we're thinking in terms of indirect utility functions as a function of prices and each individual's income, where the income of individuals, or really the sum of income of individuals, is equal to the aggregate income. This is just an identity through the mechanics of just how things are. Now that we have our definitions out of the way, we're going to go and make a proposition. A proposition is just like a theorem. We're going to suppose that for each level of wealth P and aggregate wealth M, the wealth distribution M, which goes from 1 to I as a function of P and M, solves the planner's problem. Then V as a function of P and M is the corresponding value function and indirect utility function for the positive representative consumer with aggregate demand, which is the sum of all individual demands, which is equal to the demand which is solved for through the planner's problem. To prove this, we're going to first note the first order conditions for our planner's problem, which is going and taking the derivative with respect to M. And that's going to give us the following result over here, where we go and we say our multiplier is equal to this result for every I. This is something that's not so crazy. You can go and write out the Lagrangian and you'll get this result here. We also note that Roy's identity for the value function we seek is defined as follows, right? Where this thing here is called the gradient, right? And we're taking the derivative with respect to every P in our price vector. One thing that we should also note by construction of the value function is that this result here is true, right? For when we're thinking about the world of aggregates, right? So we can think about this as maximizing some V with respect to M over here, and this is just going to spit this result out. It's not really so remarkable. I think one thing that we should know is that this is the derivative with respect to aggregate M as opposed to MI. So you can again write out the Lagrangian for our planner's problem there. Noting our first order condition with respect to PL, which is the price of some particular good of our planner's problem, and appealing to envelope theorem, which this envelope theorem, right, it's not going to be the one where only direct effects matter, but it's going to be the second envelope theorem where we can use our Lagrangian to go and analyze changes in our problem, albeit directly. So what we're doing here is that this here, let me go pick a lighter color, is going to be A-OK. And we get, this result down here, keeping things in a little bit of a quasi-vector notation with also a summation term. So subbing this result into Roy's identity, we go and we get the following result. Okay, this is fine. This is the crux here, right? we're going to recall our identity for lambda here, right? Because remember, lambda could be equal to this guy up here, but it's also equal to this here, vi as a function of mi, right? So we're going to go and abuse this as a sort of equality between the two. Subbing that in there, we go and we get the following result. Cleaning this up, right? This is exactly Roy's identity with a summation symbol in front of it. So what we end up going and getting is that our demands, which is derived through our planner's problem or our representative consumer, is going to be equal to the sum of all of our individuals' utility maximization problem, and in turn their sum of demand equations as well. So just a little postscript. The crux of the proof here relies on the facts that our first order condition for our planner's problem is identical to our household's first order condition through lambda. We are able to abuse this since lambda could take on any value. What we should walk away from this proof is that we can use the planner's problem to investigate optimality in economics models. So that's really, the main thing that needs to be illustrated through this proof. So I hope this video helps. I hope it was clear. I hope it was insightful, and I hope it was fun. I will see you next time. Take care.